Okay, so here in chapter 10, we are comparing two groups. So this is going to be similar to chapter 8 and 9 when we're doing confidence interval and hypothesis testing, but now we have two groups. So we're going to have to take these two groups and combine into one group so that we can find the probability of something like the area under the normal curve. So in order to combine two groups, we're looking at chapter 6, but a very minimal amount of chapter 6, so don't worry. So here are our learning targets. Describe the shape, center, and spread of the difference of proportion groups. Determine if conditions are met. To do inference, the conditions are the same, but now we have to do it for two groups. We are construct and interpret a confidence interval for the difference between two proportions. We're going to calculate standardized test statistic and p-value, and also perform a significance test. So, defining our parameters has always been very important, but now we have subscripts. Okay, we have two groups, so we can distinguish them between a 1 and a 2. Or you can use letters if it makes more sense. Here we have school 1 and school 2, so it's easy to do P1 and P2. So we're talking about homework that is turned in last week or last night. School 1 has 70% of its students turning in their homework. School 2 is 50%. So counselors decide to do a sample and see if there truly is a difference in the proportion of students turning in their homework. So school 1 has a sample of 100 and school 2 has a sample of 200. So just looking at the shape, center, and spread of them individually, remember your normal condition is that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. Well, now you have to do it for both groups. Then you have your formula for the standard deviation. You must do it for both. And you have your 10% condition. Do it for both. So you just doubled your conditions, really. So, what can we say about the difference between these sample proportions? So, if we take what they got from their sampling, so information that was given is counselor from school 1 found 72% turned in homework, whereas counselor from school 2 found that 47% had their homework. If we just subtract them, it gives us this 0.25. This is a simulation, or this dot plot is a simulation of the actual distribution. And notice that its center is actually at 0.2. So where's the 0.2 coming from? Well, 0.2 is the difference between the population values that it gave us. School 1 was 70% and school 2 was 50%. So that's telling us to find the actual mean of the center of the difference of the two groups is to take the parameter values and subtract them. Again, we've learned that in chapters 6 and 7. Then the standard deviation, remember, in order to combine random variables, you add their variances, variance plus variance, so that looked like sigma squared plus sigma squared, standard deviation squared. But because we squared them to get variance, you then took the square root. So that's what these pieces are. Those are the standard deviation squared, the variance, add together, and then take the square root. So now we have the variability, the spread. So all together, we know it's a normal distribution if all four NP and N times 1 minus P values are all greater than or equal to 10. We can find the mean of the sampling distribution by simply subtracting the parameter values that are given. And then as long as our 10% condition is met for both samples, then we have our formula for standard deviation. So all these little pieces we need for confidence intervals and hypothesis testing. So here's another example of just checking conditions. You have goldfish. Bag 1 has 25% red crackers. Bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Your first sample is 50 from bag 1 and 40 from bag 2. This is our difference, p hat 1 minus p hat 2. So what is the shape of the distribution? Find the mean, calculate and interpret standard deviation. So the shape is normal because we check that all are greater than or equal to 10. The mean is just the difference of the 25% and 35% that were given. So we have a negative 0.10. And then We check the 10% condition for both bags. They both check out, so we can use that formula to find the variability. Then it told us to interpret that standard deviation. So the difference in the sampling proportions of red goldfish crackers typically varies by about 0.097 from the true difference in proportions of negative 0.10. Alright, so what does this mean for confidence intervals? Remember, you have your three conditions for confidence intervals: random, 10%, and large counts. So again, you're going to have to check that for each of the groups that we're dealing with. So here we're talking about adults from the US and from Germany and their importance of brand names when they're shopping. Can you buy the off-brand, or do you want that name brand? So 2,309 US adults were surveyed, and 26% said that brand names were important. And then 1,058 German adults were surveyed, and 22% said that it was important to them. So here they've defined, instead of P1 and P2, they have PU and PG. PU is for the US and PG is for Germany. So again, you don't have to use numbers to help identify what the different p-values are, but you still must define them. So check that the conditions for calculating a confidence interval are met. So they're both random samples, 10%, but each of those samples are definitely less than 10% of all the adults in those nations. And then we can check that each of the large count values are greater than 10. So now you can actually construct an interval. So this first line, that is what's on your formula sheet. But you need to think of it as an entire formula, piece it together. So we know that the statistic is a difference between the two statistics from each of these samples individually. The z-value is the same if we're doing 95%, 99%, or whatnot. Standard deviation. So standard deviation, if we know the parameter values, then we use those. If we do not, then we will use the sample values. And remember, that's called standard error. So in all, you need to think of it as this entire formula. We're really not going to know what the parameter values are, because if we do, then we can just compare them by face value. We're going based on samples. So one thing to remember is we have random sampling and we have random experiments. So our 10% condition is necessary for sampling. It is not necessary for experiments. And also when we have the random condition, we're talking about random sampling, whereas this is going to be random assignment. We're going to be assigning people to two treatments, and it is the fact that they are assigned randomly that checks off the random condition. So patients with lower back pain are often given an anti-inflammatory drug like naproxen. Well, they want to know if taking Valium with the naproxen would actually affect their pain relief, meaning making it better. So to find out, they have 112 patients. They put them into two treatments. One that takes naproxen and the Valium, and the other that's naproxen and placebo. Making sure that they have a second thing that they take, but they don't know if it's the actual drug or not. So after 1 week, 39 of the 57 subjects who took both reported reduced lower back pain, compared with 43 of 55 subjects that had the placebo. So construct and interpret a 99% confidence interval for the difference in the proportion of patients like these who would report reduced lower back pain after taking both of them versus having the placebo. And then part B, based on the interval, what can you conclude? So 99% confidence interval for the difference P1 minus P2. And here we define what P1 and P2 both are. Now, this is a two-sample Z interval. So if you're going to use your calculator to do all of this math work, make sure you're using the two-sample Z interval function. Random, they were randomly assigned into their treatment groups, and then we check the large counts condition. Remember, we do not have to do the 10% situation here. Now we calculate. Find your p-hat1, so that was for taking the Valium with the naproxen, and then the p-hat2, that was the placebo. Subtracting them gives you your statistic. We have our z-value based on the 99% confidence interval, and then we find that standard deviation. So it gives us a final interval of negative 0.312 to 0.116. So we can conclude by saying we are 99% confident that the interval from negative 0.312 to 0.116 captures the difference in the true proportions of patients like these who would report reduced pain after taking naproxen and Valium versus after taking naproxen and a placebo for a week. So, based on our interval, what can we conclude about whether taking the Valium along with the naproxen actually helps reduce it? So, when we're talking about the difference of things, we first are assuming that there is not a difference whatsoever. So, if we find the value of 0 in our interval, then we have reason to believe there's not a difference between these two groups. Now, remember, our interval is not guaranteed to capture the actual value, but we can be pretty confident, and in this case, 99% confident. So because the interval includes 0 as a plausible value for the difference, we don't have convincing evidence that taking Valium along with naproxen affects pain relief for patients like these. We just had some patients that didn't see relief or whatnot, so we're not really sure. So again, never suggest that you believe the difference between the true proportion is 0 just because it's in the interval. It's just plausible, not a guarantee. So again, in your calculator, it's a 2 proportion z interval. It'll ask you for particular information, and then it'll come out with your interval. It comes out with the statistics as well. So now significance test. Same idea. Things haven't changed too much. It's just the combining of them. So in our claim for two groups, we're going to claim that there is no difference. So P1 minus P2 is 0. Another way to look at that is P1 is equal to P2. I suggest looking at this situation where we write P1 is equal to P2, because when you're using your calculator to then do your alternate hypothesis, you have situations where it says P1 is less than P2, P1 is greater than P2, or that P1 is not equal to P2. You can still do the original subtraction situation, and they will look like P1 minus P2 is greater than 0, P1 minus P2 is less than 0, or P1 minus P2 is not equal to 0. And they all then refer back to the same thing. They mean the same thing. But using your calculator, it's going to be in this notation here to the right and not to the left. So you have your three conditions, random 10% large counts, just like before. So I'm going to skip the idea of checking conditions and only talk about stating the hypotheses. So researchers designed a study to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 missed breakfast today. At School 2, 150 students were in the sample, 26 missed breakfast. There are more than 1,500 students in each school. Do the data give convincing evidence of a difference in the population proportions at the alpha 0.05 significance level? So part A, we're just stating our hypotheses. So we have that P1 minus P2 is equal to 0 for the null, and the alternative is P1 minus P2 is not equal to 0. It did not state that one school had a larger proportion than the other of students not eating breakfast, just if there was a difference. And then we defined P1 to be School 1 and P2 to be School 2. So when you're doing your significance test, remember that you have your formula to find your standardized statistic, but you need to think of it as an entire formula with all the pieces put together. These are the same pieces as we had from our confidence interval. Now, it does say here that we have P1 and P2, not P hat. Here's our statistic. These are parameter values. Be careful. Now, are we going to know the value of P? Not necessarily. This is called a common value of P. So when you're doing hypothesis testing, you're going to do what's called a pooled or combined p-value. Or, sorry, not p-value, a proportion. And the way that you're going to do this is add fractions the way you always wish you could. Okay, so let's look at an example. This is still the breakfast. All right, so explain why the sample results give some evidence for the alternative. Calculate the standardized test statistic and p-value. And then what conclusion can you make? We have from school 1, 19 out of 80, and school 2, 26 out of 150. When you take those two proportions, subtract them, we get something that's not equal to 0. Therefore, we believe that there is a difference between the two. So we do have evidence in favor of the alternative. Part C, calculating the standardized test statistic. So you have your statistics from before that you're subtracting. You have 0. What is new is this denominator with the pooled p. That's this value up top, where we take the statistic or the proportion from each of the groups, P1 and P2, and you add. But you get to add the fractions straight across like you will always like to do. That's where you get the pooled p-value, or the pooled proportion, for the denominator. So then you get a z-value of 1.17. So we go to our table, we look up 1.17, it gives us 0.1210. It's a two-tailed test because it's not equal to 0, it's not equal to. So we have to multiply by 2 to get our final p-value. Again, you can go in your calculator and use a two-sample z-test, and it'll give you that p-value that you're looking for. So because the p-value is greater than alpha, we fail to reject. There is not convincing evidence of a difference in the true proportions of students at school 1, school 2 who skipped breakfast today. So on your calculator, a two-proportion z-test asks you for certain things. Here is the notation that your calculator is using. So that's why I was suggesting the right-hand side situation instead of the left. It'll give you your z-value and that p-value. Now remember, if you're using your calculator, you do need to supply certain pieces of information to get full credit. You need to give the name of a test. So this one is a two-sample z-test for the difference of proportions. You need to give the test statistic, and you also need to give the p-value. So once conditions are all met, then you have your formula, you calculate everything. So putting it all together, here we have high levels of cholesterol in the blood are associated with high risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? So if I'm taking a cholesterol medication, does it reduce heart attacks? So there's two treatments. There's 2,051 men who took the drug to reduce their cholesterol, and then a control group of 2,030 men who took a placebo. During the next 5 years, 56 men who took the drug and 84 men who took the placebo had a heart attack. So do the results of the study give convincing evidence at the alpha is 0.01 significance level that the drug is effectively preventing heart attacks? Part B, interpret the p-value. So remember, does it provide convincing evidence? We have to give an entire hypothesis test. So our null hypothesis, we have P sub G minus P sub C. The G is the drug and C is the control group. So the alternative is that difference is going to be less than 0, because we would expect the proportion who took the drug that had a heart attack is less than the proportion who had the placebo. So it did not tell us that we had to subtract in this order. So we could have set it up to where we had P sub C minus P sub G equals 0 for the null, and then PC minus PG is greater than 0 for the alternative. Here, we would think that those for the control have more, so when we subtract, we get a positive value. So it doesn't matter the order that you subtract, but please do realize that the order you subtract is going to help you identify whether you're using a less than or greater than an equality symbol. Then in defining what PG and PC are. Alright, so it's a two-sample z-test for the the difference in the proportions. They're volunteer subjects that were randomly assigned to their treatments. And then you have your large counts. All the numbers are greater than or equal to 10. Then we have our statistic for the drug group. Then we have the placebo group. And then we have the pooled proportion value. Plug everything into our formula. We get a final test statistic of negative 2.47. Go to our table. It gives us a p-value of 0.0068. Or again, you can use your calculator. So because our p-value is less than alpha, we reject. There is convincing evidence of a lower heart attack rate for middle-aged men like these who take the drug than those for taking only a placebo. So interpreting that p-value, assuming that the null is true, there is not a difference. There is a 0.0068 probability of getting a difference, drug minus placebo, in heart attack rate for the two groups of negative 0.141 or less just by the chance involved in the random assignment. This negative value is the difference of their statistics. And that is chapter 10. So, or at least section 1. Again, it's the same thing that we've been working on with chapter 8 and 9. We're just combining two groups now.